Well, hi and welcome to my shop here. This morning I'm going to be focused on replacing just three particular capacitors in this radio, and that's these three paper ones that are left. Maybe I can call these cardboard capacitors that are left. First, I'm just going to show you a peek out into my backyard. A little bit of snow out there. Wow, we don't have very much here compared to other locations. I live in the snow belt, but we didn't get belted with snow, and it looks like the current snowstorms are going to miss us. But I know a lot of people are buried in snow all over North America, and cold weather here. So that's what's happening outside. Now, before I started the video rolling, I thought I'd take a couple minutes and identify the three capacitors on the schematic, just so I'm aware of what these capacitors do and what influence they might have on the radio. And that took me a long time, because once again, the schematic can be misleading in terms of the location where it shows capacitors. It can show them schematically almost anywhere. Physically, they're somewhere quite remote in the radio. And also, some of these capacitors are utilizing spare terminals and things like that on the components below, and that just makes it really quite difficult, quite time consuming. I spent quite a bit of time just making sure I knew what these three capacitors are. Part of the confusion is this one is a 0.1 according to the schematic. Now this one is a 0.05, half that size according to the schematic. That looks pretty good. Looks like about half the size. And this one is also 0.1 on the schematic, but here in the radio it looks like a 0.05. And that was part of my confusion. So stuff happens. What can I tell you? So we'll take a look at the schematic for each of these three capacitors and just talk about their purpose and why they're in the radio. Okay. So the first one, the big one, the 0.1, is C18. Just take a look. There it is right there. C18.1. It's hooked up to the screen grid. Now you notice there's a great big one here, a 10 microfarad capacitor. This is the first one I replaced very early on when I started working on this radio. This was the capacitor that was not connected. It was floating. You're going to see I've got it in my hand here, 10 microfarads. So I've corrected that problem. I've installed this little guy here. But this is the one we're looking at now. So why have a 10 and a 0.1? Why not just, isn't a 10 good enough? And the answer is no, because the 10 is a electrolytic capacitor. Electrolytic capacitors aren't very fast, so they don't do a really good job at high frequency. So we could throw in a smaller capacitor that will work properly at high frequency to compensate for the weakness in this kind of capacitor. Or these big electrolytic ones are usually dealing with 60 cycle hum down in the power supply. So that's what's going on there. So that's one of them, 0.1. Now another one I'm doing is C24. This is the one that's in the middle of the radio, if you like. And there's where it says 0.1. But in fact, I'm pretty sure, maybe I'll be surprised, but the capacitor that's in there sure looks like a 0.05 to me. And the last one, number 22. That took me forever to find it. It's installed right around this tube, C22. But on the schematic, C22 is way over here somewhere. It's way over here. 0.05, which is what I think it is, a 0.05. The only thing that saved me, and thank God I remembered it, is this diagram. This is the diagram that saved me. So I was able to find that last capacitor. So without it, oh my gosh, I don't know how long it would have been before I would have realized where this is in the radio. Where this is on the schematic, rather. On the radio, it's over here. But in the schematic, it's stuck way over here. So, okay, enough of that talk. What does each one of these do? So going back to the first one, so this is the screen grid line. This is shared by quite a few tubes that have screen grids. Right to the screen grid. It's just a wire. And we go back this way. Again, straight to the screen grid. So in fact, the screen grid circuits for these tubes are being silenced by these capacitors here, located here. This isn't just about this tube, it's about all of them. It's about the entire screen grid supply line. So that's all that's doing. It's just trying to remove any AC signal that might be present on the screen grid and try to turn this into nice pure DC. That's why you need this big 10 guy here to do that. So let's go look at 24. So C24, another fairly large capacitor, is on the cathode of this tube, and it's bypassing this resistor. You know, they really should have drawn this capacitor right down here beside it, or even drawn it around it to make it more apparent what it's doing. But that's what it is. It's the bypass. This 270 ohm resistor is the cathode resistor providing bias for the tube, using cathode biasing on this tube. So that's a bypass. So I'll talk about what happens if each of these are weak. So I go over here, C22, 0.05, smaller capacitor. It's on this line. And this line goes to the grid, right to the grid. But the capacitor is on the other side of this huge resistor. So this doesn't feel much effect from this capacitor on the far side of this resistor. So this capacitor must be working more on this part of the line. And what is this line? I think we're going to discover that this is the ABC line. So at this point, you notice the note, oscillograph connections vertical high here. This is basically the output of the detector. I could put a voltmeter here. I don't need to put an oscilloscope here, but we may do that. The point is, the ABC voltage is developed here in this fairly low impedance circuit. If you hook this low impedance circuit directly to these grids, all the grid impedances will be pulled down. The radio's not going to work well. So you stick a great big isolation resistor in here, and on the far side the impedance is very high now, and the grid's like that. And that's what this guy's doing. So what's this 0.05 doing? I'm pretty sure this is the ABC speed capacitor, if we can call it that. So as the ABC voltage drifts up and down, picturing yourself listening to shortwave now. If you're listening to a local AM broadcast, unless it's at night and fading in and out, you'd have to listen to shortwave to really get the benefit of this whole arrangement. So the shortwave signal is going up and down, the ABC voltage is developed going up and down, the voltage on this line is going up. Well, it's going down and further down. I mean, that's a better way of putting it. It's going down and really down. It's becoming negative. And it has to charge this capacitor, which is squeezed between this big resistor here and this guy here. That's interesting now. The effect of this capacitor in smoothing out, slowing down, holding on to the ABC voltage, however you want to look at it, is supplied right to the magic eye. But this first tube is on the far side of another very high resistance resistor. Now bear in mind there should be no DC current flowing in here. This resistor sits here looking pretty much like nothing. There's no current flowing. Right to the grid. So this could be a way to isolate this tube away from the rest of them. Something like that. Okay, so just to go through again really quick, this guy is the ABC capacitor. That's a typical size for an ABC capacitor. If this guy's weak, let's say this thing was shorted, well, I wouldn't even say that. If this has no capacity, it's not doing any action, then the ABC is probably, I think you'd be open to maybe oscillations and everything through here, too. Maybe it's doing a little more than just kind of buffering the voltage. And so this guy's also quieting the screen grid. And the last guy, bypass. They're all doing different things. Interesting. They're all doing entirely different things. So I replace all three of these. I'm really having three significant different effects all at once. And I want to do this more separately. So if this guy, well, why don't we start with this one? If this guy was weak, if it wasn't capacitoring at all, if there wasn't any AC grounding happening here, then some of the AC signal being developed in here, the actual signal we're trying to tune, will be lost in this resistor, be wasted in this resistor. So if this is not doing its job, this tube's a little quieter on the output. C24, okay. So I think what I want to do too, so C24 is this one. This is one that I think, on the schematic it says it's supposed to be 0.1, but it looks like 0.05. So what I'm going to do here is I'm going to fire up the radio. We'll make a few measurements around this capacitor if we can. Yeah, I gotta think. Well, anyway, I'll get things set up. So we're gonna get something set up here. Let's get something set up, Jeff. Okay, so here's what I've got going. We're going after this capacitor. We'll look at it again on the schematic in a moment. This is C24. This is the bypass capacitor around the bypassing around the cathode resistor. So you can see the scope connection here. The scope is connecting to the top of that capacitor, the ungrounded end, and the signal you see up here on the scope is what is at that location, and what you're hearing, of course, is coming out of the signal generator over here. It's just tuned into the radio. Let's just check the tuning and everything. The signal reaching the scope is just not quite high enough to cause a trigger. Still not high enough. So I continue to have trouble with the triggering on this scope, but we won't worry about that. Oh, there we go. Standing still now. I'll change the frequency. You keep your eye on the scope there, and you'll see that that is what we're listening to. I'm going to change the modulation percentage from 30%, which is a normal test level, upwards. We'll see what happens on the screen there. So that's about 100% modulation. I'll show you on my signal generator. It claims to be 50% modulation at that point. And it doesn't go any higher, because I guess you don't normally go higher. So we'll go back down to 30. That all seems to make sense. Usually things don't make sense, so. But here's what doesn't make sense about that. In fact, I think that shouldn't be there. I think that signal you're looking at, right there, I think that should be flat. I think this big capacitor should be knocking all that AC out. That's what's across the cathode resistor. I don't think you want any of that across it. So this is suggesting that capacitor is not doing its job, or maybe it's undersized, because remember the schematic says it should be a 0.1 when in fact it's a 0.05. So as a matter of experiment here, if I grabbed a 0.05 capacitor, I don't think this is one, and just temporarily put it across the capacitor that's there, because I think I can get at the, I think I can do this. Let's try it. 0.05, here we are. So if the capacitor that's in there is a 0.05, then I'm doubling it. 0.1. If it's a 0.05 and it's not working well, then I'm changing it, basically restoring it to 0.05. I'm going to have trouble looking up at the scope. The radio should get louder too. There we go. I'm in contact. See that? See the line drop to nothing? That's from adding this capacitor. That's what we want to see on there. So that suggests this capacitor is definitely bad. Okay, without changing any of the test equipment, I'll remove that capacitor. We will test the capacitor. Then I will install the new 0.05, and I better get this one out of here or I'll install the wrong size. It's sitting there. Let's nip it out of there. I'm going to relocate this to here. This wire here. There we go. Definitely. And this one here. Point 1. So this is a bypass capacitor. It's probably not good for the higher voltage. And it says 300. It says 0.1, 300. That's probably the voltage rating, 300. This is probably a much higher rating here on this one. That's why it's so much larger. So it is a 0.1. So I just added a 0.05, half what this should be, and it made a big difference. This thing must be a 0. Let's go see. This is pretty interesting. I'm getting a kick out of this. A lot of times I try to do these things and they really, frankly, they don't amount to much. And what I'm talking about is, you know, testing components before I replace them and things like that. Sometimes it's just the story doesn't quite come out the way I expect it to. That's just another way of talking about life, isn't it? Okay, he's hooked up. First test we'll do is the we'll test it for leakage. 50 volts. Huh. Well, there's no reason to test it. Well, I want to keep that on there. Keep that on there. No, there's no way that this is not even opening on 50 volts. So this guy's in terrible shape. No reason to test it for capacitance when it's this leaky. The capacitance reading doesn't mean anything when you have a really leaky. That's my experience. You can get a reading on there, but it won't mean anything. In fact, sometimes you'll get a higher reading than the rated capacitor. I think the test is totally bogus. So we need a 0.1. Uh-oh, 0.1. We've got a 0.1. This is going to be a 0.1, I think. Pretty sure. Me being pretty sure often doesn't really mean a lot. Where's my capacitor meter? Hey, that quickie capacitor meter. Where did it go? It's gone away. Okay, well let's try it back on this one. It's still on, so we might as well. We can use this. Brand new capacitor. Is it a 0.1? I could also look up, you know, it's 104. I'm sure it's 0.1. But let's have some fun here anyway. So 0.1 will be on this scale. And watching the eye. Boom, right there. Where are we? 0.1. Okay, no question. I just like to double check these things. Because sometimes I get crazy thoughts in my head. That's off. Okay, so I'm going to install this, and then we'll repeat that test. Let me just get it installed here. Okay, so that's a new C24 in there. My capacitor is rated for 600 volts, not 300. It's still fairly small. Scope hooked up. Let's give them a go. Everything left the same. Switch on. So what we're hoping to see on the scope now is basically nothing. We want this line to stay straight. That doesn't sound particularly nice here. full power. That's probably why. So the radio is receiving a little bit of radio signal from the big loop antenna, which is still connected, but look at the line on the scope. It's as flat as can be. So what that means is we have created an AC ground point above that resistor that goes to ground, and so it's good. AC is bypassing the resistor. That's the best way to put it. So that was successful. I'll tune the radio a little bit here. So that certainly shouldn't have affected the tuning at all. So now we're going for the next capacitor. Next capacitor, well, we've got two here to choose from. Let's jump on the schematic and pick one. So C22. So C22 is the AVC capacitor. I think this one will have the least effect, I think, unless this is an absolutely shot capacitor. I'm going to guess. So let's go for the other one, the 0.1. That's C18. That's right here. Now this guy's important because he's helping to quiet the screen grid of all these front end tubes. And if you let some high frequency RF fiddle around on here, you could get some kind of feedback situation developing or something like that. So we'll go after C18. That's the big fat one. C18, but we're not going to do it with the radio operating, that's for sure. C18. Let's put the radio back on. Let's take a look at what is. So in the same way the last capacitor was supposed to snuff some stuff out and we could see the stuff. I replaced the capacitor and the stuff is snuffed. This one's also a stuff snuffer. That's a new technical term. You guys can use it all you like. So the high end of this capacitor, I'm pretty sure, is up here. Can you see the scope? You can see the scope. Make a connection. Let's see if it jumps or something. Well, there's something there. Get on there. Okay, let's go back and look at it. So this guy's job is to snuff RF. And that would look like an RF voltage right here. I'm trying to snuff this with both a great big 20 microfarad and this 0.1 that we're hooked up to. That probably shouldn't be there. So I can repeat the same experiment just by taking a 0.1 capacitor. I'll do with a 0.1 this time. Take a 0.1 and we'll just parallel it. It's only supposed to go to the chassis, so I can just touch the top and the chassis at the same time. Here, you can watch me do this. Okay, holding on to a capacitor is just not the safest thing. That'll be the ground. Watch out for the other end. And now we're going to swing it down. I don't want to be touching anything. Okay, are we ready? Watching the scope. Ooh, little pop there. Did I see it disappear? Much less. Much less. Not completely disappearing though. Now if that old capacitor is good and it's got 0.1 in it and I just changed this from 0.1 to 0.2 by paralleling in another one, then yeah, you'll see that effect. But then if I cut out the original and put in the one I'm holding on to here, it'll look like this again, because it's just 0.1. So what we'll do is we'll lift one side here and bring over the leads to test this capacitor before we remove it. No, we're going to remove it. We will remove it. It's got to go. Come on. Come on. No hope for that thing, Jim. Come on. Okay, power is off. This almost looks like a electrolytic. Point 1, 400 volt. Okay, let's give him the works here. Give it to him. Let's give it to him. Let's show him who's boss. Volts. 50 volts to start with. Now you might be able to see that my tester says 25 there, but in fact it's 50 on these machines. And that's actually a mistake. And I've checked it. It is 50. Around 50. Roughly 50. 50 is double 25. Ready. Hit him. Whack. He's trying. Well, it didn't open all the way, and I'm sure at 150 it's not going to open. He's a leaky guy. So this means it's additional resistance. I'm sure the resistance of this is really high. We can actually measure it on here. Let's give it a moment for the charge to bleed off, and then we'll try using this to measure the resistance of this capacitor. Okay. I very seldom use this. So this is R times 100. Does it open? Oh yeah, it opens way up here. When this guy works at the end of the run, you can't trust it. So it opens again on a different scale. So if you believe this, it's 1,000 plus ohms, but if we set this to R times 100, we get the same spot. So we just can't rely on this test. I would think the resistance of this is just incredibly high, even though it's leaky. So I'm not done yet. Virtually never just check the resistance of a capacitor, but let's give it a try. See what happens. It's got to be pretty high. I'll put my meter on 20 meg ohms. Huh. Oh, see the negative sign? So it's carrying some voltage. Hey, here's another test we're going to do now. We're going to put a short circuit on this. We're going to test to see if this capacitor has turned into a little battery. A very crappy battery. So I want to ground it out so any residual charge is dissipated, although because the capacitor is leaky inside, it self-dissipates. I just want to be sure. Now we're going to hook up the voltmeter. I'm going to use clip leads to do this. A little experiment here. Put this on here. Lock this on. DC, say 2 volts. And we should see 0, of course. And I'm going to lift one of these leads off, and if that thing comes off 0, there's only one, well, there's still 2 possibilities. One is there's still residual charge in the dielectric, and the other one is there's a galvanic voltage. There'll be a way to tell them apart. Here we go. Going up. Anybody want to try to explain that? Half a volt. Oh, I'm glad I did this, because I've demonstrated this effect a few times, and sometimes this demonstration doesn't go all that well. So I'm suggesting that this is a half a volt battery that can produce enough current, enough power to drive my meter, because the meter takes almost nothing. It takes something. Almost nothing. If we disconnect the meter, this voltage would go up even higher. Let's put the short on. Let's see how convincing I can be of this. Because I've never read about this anywhere. I've never read about this. Yeah, I see it all the time. Here we go. Once again. Up she goes. So I think it can only be one thing. You know what else we can do? We can reverse the leads on this and see if that's a negative. It's just it's just that much more convincing. In fact, I'm going to revert. I'll reverse them here. Okay, so this doesn't come up negative. This clip won't be published. There it is, negative. That's really convincing. Okay, so if anybody's had any doubt, you see me do this demonstration and wonder, well, what the heck are you doing? What are you proving here? What I'm proving is this capacitor were involved in a high impedance grid circuit. This voltage would be in there probably. We won't test it any further. Bad actor. We're going to put in the good actor. Not this one. This one. I'm going to put them in there. Okay, so I'm going to install that in this spot and we'll make another test. Okay, new capacitor is in. Brand new C18. Oh! There we go. At least once a session I have to drop my solder on the floor. Okay, on to the high end of the capacitor. Scoping. Make sure. Okay, good. We're ready. Dim lights on. Scope coming to life over there. So it's gone off the screen because there's a DC voltage developing in the radio. Just like I said, there's that signal. It's not quite as big as it was, but it's still there. So we could be seeing the effect of the other capacitor. There's supposed to be was it a 10 microfarad capacitor there? Wait a minute. I replaced that over here. That's taken care of. Well, that's what we got. It's a little bit better than it was. We don't have a leaky capacitor in there anymore, so that might actually be a more significant improvement than we're realizing when we look at the scope. One more to go. One more to go. Last capacitor is C-22 ABC capacitor. So first of all, this is in a real high impedance location here. It's between this big guy here and this guy here. If this thing is at all leaky, the little bit of charge that's in here will flow out and it'll really ruin the voltage in here. If this guy's a little bit leaky, because he's facing these great big capacitors here. How can we tell? How can we tell that? We can always take a test on the top here. The problem is the reading, taking the voltage reading, the meter can drain the charge out of this line between these two large resistors. So the meter is about 10 megohms. And these resistors are 2 megohms. So I put a voltmeter on here. What I will read is not what was really there. I will read what it is when the meter's hooked up. I could go up here. This will give an even poorer idea of what the voltage is here, because now the pressure here has to work its way through 2 million ohms to get to your meter. The meter's 10 million, so you're losing 20-25% there. I can measure back here, but if this voltage on this line is being pulled down, and by the way, if you pull this voltage down, this one goes with it. And watch out, I'm using the word down, but down doesn't mean negative, it means less in this case. So I measure here, I won't see anything that's happening on this line. So my only hope is to hook a voltmeter here, read what it is, feed in a signal, generate an AVC, stabilize the whole thing, shut it all off, change this capacitor, turn it back on, see what happened to that voltage. That's the best way of doing this. Now let's do it. Let's do it. So first I think I better turn it off. Oh, I did that last thing on on the dim setting, but that's okay. That's okay. Now, this guy over here. So we want to read the voltage at this location. I think I'm going to use my which meter should we use to do this? The voltage may vary a little bit. Let's use an indicating meter to do it. That's a meter with a pointer on it, like that one, or like this guy. I'll put him over to DC plus. What is the voltage there? The voltage there is going to be very low, negative voltage. I think it's ABC voltage. Yeah. What am I thinking? Okay, so we'll put this on 15 volts full scale. Negative reads upscale. Find the leads for it. Then we want to hook this up. I use a clip lead. To the active end of this capacitor. Active end. So one end should be grounded. Okay, so it's this end that's grounded. I can see that this is the active end coming down. Tying to what I'm pretty sure is a spare terminal down here, which is part of why I found this. How can I get in there? I found this so confusing. Okay, I'm going to move this over a little bit. Did I get it on that? Got it on the wire. Get it on the terminal. There. Okay, so voltmeters hooked up, basically monitoring that piece of the AVC circuit in between the two big resistors. So we turn the set on. We should see a negative show up there. The scope is still connected where it was. That's okay. Why wouldn't we put the scope on there? It's just that much more load. Scope has a 1 × 10 setting here, so you can get a pretty high input impedance for the scope. Let's try one thing, let's see what happens. Is everybody ready? I'm ready. Okay, here we go. The meter may do a couple of funny things at first, but it should go up. It should go up. There's the radio. Yeah, see this. Excellent. Now, one way we can tell if the meter is loading the circuit is to disconnect the meter, hear what happens on the radio. I didn't hear a thing. Now I'm going to hook it back up. If the voltage on that line has gone up, and if my meter is knocking it down, we'll see a higher reading and then a drop off. It'll happen very quick. Now there's meter, pointer, momentum throwing it up there too. So here we go. No, I didn't see anything like that. The radio didn't change much. I think it's a completely valid reading. Let's tune the radio and make sure it's ABC that we're seeing. This whole ABC thing only works because certain tubes are designed to enable this small DC voltage to be utilized to change their gain. You know, it's a trick. What can I tell you? You know what else is a trick? It's almost 1 o'clock. Holy smokes, I'm late for lunch. I'm having too much fun today. So what we'll do is we'll take a note of what this voltage is. And we'll change that capacitor, and then we'll take a note of what the voltage is again. And make sure everything is tuned just right. Let's just make sure of that again. Very highest voltage on that meter over there. Now the capacitor itself makes this tricky. Look, I'm getting a little more there. Okay, that's the max. Okay. Power off. Leave all the equipment just as is. Out comes this guy here. And we're going to nip him. I'm going to nip the wire right now, but I think we're going to go right to the terminal when we actually put the capacitor in. Out come. Let's go over to the doctor's office here. My leads here. On this unit, the center terminal is the positive one. There's no polarity on the capacitor, but it's good to know for electrolytic tests. Okay, we're on. 50 volts. Do you leak? Oh yeah, you leak all right. No reason to go any higher with it. You can't even support 50 volts on my eye. Okay, you could say with a wink of an eye. We determined this guy is bad. 0.05, just as it says on the I think this is a 0.05. Just like it says in the schematic. 0.05, say 503. Yeah. So I'll stick this guy in, and we'll see what happens to that ABC voltage. I'm having a great time here. Okay, are we ready here? Keep that meter on camera. I'm going to switch on the radio. You know what? I don't remember what the voltage was. Oh, son of a... Okay, I think I remember roughly. There we go. Patience. It's very similar voltage, but I think it's higher. Son of a gun, I can't remember the exact number I had. Ah! Higher as in slightly more negative, which is what we would hope for. Let's tune it a little bit here. Okay, let's pretend it's a little higher. Good. Great, so every one of these capacitors has had a beneficial effect on the radio, even though the radio was working fairly well. Got to be working better now. The last thing we'll do is we're going to listen to this radio just a little bit. So I'm going to take off the signal generator. And we can continue to watch the ABC voltage over here and see if we can pick something up. Something in here. Or am I on the wrong end of it? You know what? I think I'm on the wrong end. I'm on the wrong end of the band. The antenna may be aimed badly. It's probably a Toronto station.
No, we don't. The family believe that. We don't subscribe to that at all. Like, that is not something that we get behind. And as much as I thought of David, which is Arthur Ryan, and Eric Javi Group, people behind the scenes that nobody knows stay up and see it. It was 4 or 5 hours that flew by, but it stuck with me. Head and heart, it stuck with me. All they wanted was our attention and conversation these war vets. So I wish very much that in future, on November 11th, Navy school boards and teacher federations can find a way to do more of this, even with all the issues and concerns.
Holding on to the gains, the S&P and the NASDAQ hit intraday highs early in the session. The S&P right now up by 9, the NASDAQ higher by 44. By 44.
That chick is my soldering iron.
16,899.
Hey, I've got this on dim bulb there still.
From its all-time high, gold is down $3, 14.53. Oil off by 12 cents, 56.74 a barrel, and the Canadian dollar up by 100, 75.58 cents U.S. At the Business Center, I'm Chris McCusker.
Hi, Alan Marion from Marion, Canada.
That's a 680, I think. That's about. Oh.
By the third period, just say, hey, you know what? Something's actually.
This is really good.
You might want to
Well, that's good. So now what we're looking at doing here is considering the replacement of these two molded capacitors. I don't think I'm going to do it. And these ones here, which are highly reliable, but one of them is cracked right through the shell. I think probably before doing any more part replacements, the name of the game now is to do 100% alignment on it, and including the short wave bands. We'll do that tomorrow, and we'll see what the real performance of the radio is, and maybe its performance is fine and this cracked shell here means nothing in terms of that capacitor. So that's great. This has been one of my most enjoyable shop sessions here ever. I hope you enjoyed it too, and I'll see you on the next video. Thanks a lot for watching.